your...
Bien, pues muchísimas gracias a todos. Bienvenidos a cada uno de ustedes. Nos da mucho gusto tenerles aquí con nosotros, a toda la comunidad de alumnos de la Facultad de Ingenierías, también a los docentes que nos acompañan el día de hoy y, por supuesto, a nuestro invitado y a nuestro ponente, el doctor Matteo Russo, a quien presentaremos brevemente un poquito más adelante. Nos da gusto tenerles y esperamos que esta conferencia pueda ser de interés para ustedes, que puedan ayudarles a obtener una visión también pues muy reciente de lo que se está trabajando en la fase de ingeniería y tecnología hoy en día. Entonces, pues nos da mucho gusto que estén todos con nosotros, conectados, y voy a darle el tiempo en esta ocasión al doctor Eduardo Esquivel, docente de la Universidad de Celaya, quien nos hará el honor de presentarnos al doctor Matteo Russo. Bienvenidos, adelante.
Excelente, muchas gracias, Daniel. Gracias por, por cederme la palabra. Muy bien, chicos, ya se están terminando de conectar todos. Les presento al doctor Matteo Russo, que va a impartir la conferencia el día de hoy. El doctor Matteo Russo, les voy a comentar un poquito sobre su trayectoria. Él recibió su grado de licenciatura y de maestría en ingeniería mecánica en la Universidad de Cassino, en Italia. Esto fue en el año 2013 y 2015. En el 2019, él recibió un doctorado europeo en ingeniería mecánica y biomecánica. Ha sido investigador invitado en la Universidad de RWTH de Aachen, en Alemania, también en la Universidad del País Vasco, en España, y también en el Instituto Tecnológico de Tokio, en Japón. Esto fue en el año 2015, 2016 y 2017. A partir del 2019 ha sido investigador postdoctoral en la Universidad Tecnológica de Manufactura, trabajando para Rolls-Royce en Manufacturing on Wing Technology, en la universidad con sede en Nottingham, en Reino Unido, que es actualmente donde él está trabajando. Él trabaja en robótica, en inspección para las industrias aeroespacial y para la industria nuclear. Por mencionar, sus principales intereses de investigación son robots tipo serpiente, diseño de mecanismos, cinemática de los robots y también ha trabajado mucho con manipuladores paralelos. Sus reconocimientos y distinciones incluyen el IFTOM John Delegate Program. Ha recibido varios premios al participar en el programa de IFTOM. También tiene varios artículos que han sido premiados por conferencias internacionales. Actualmente es miembro de la IEEE y también de la Asociación de IFTOM Italia. La conferencia que nos va a presentar el día de hoy se llama Snake-like Robots for the Inspections and Maintenance of Aircraft Engines and Nuclear Facilities. Muy bien, los invito a prestar atención. Al final de la conferencia haremos una sesión de preguntas donde tengan espacio ustedes para cualquier inquietud poder compartírselas. Les comento también, la conferencia va a ser en inglés, se impartirá en inglés, entonces al final los invito a intentar hacer sus preguntas en inglés. Si hubieran alguna complicación, no hay problema. El doctor Matteo entiende un poco del español, la pueden hacer en español o aquí apoyamos y ya él les responderá seguro en inglés. Ok, excelente, doctor Matteo.
Muchas gracias, Eduardo.
Gracias. Thank you.
So, thank you. Sorry if I'm going to speak in English, but my Spanish, unfortunately, is enough to understand, but not to give an entire technical presentation in that language. So, as Eduardo said, I'm going to present today some of the snake-like robots that I design and work with And these snake-like robots are mainly for the inspection and maintenance of aircraft engines and nuclear facilities. So I work with the nuclear and aerospace industries. So first of all, I would like to briefly introduce my research center. My research center is called the Rolls-Royce University Technology Center in Manufacturing and On-Wing Technology. And it's basically a Rolls-Royce laboratory within the University of Nottingham. So we are a hybrid research center that works together, both with academia and industry together. It is a bit older than 20 years. It's now 22 years old. And we mainly work on advanced manufacturing, fixturing and tooling, and on-wing robotics. And I will explain exactly what that is in a while. The motivation behind this research center is the need for a constant maintenance and repair on aircraft. I don't know if you know this, but Rolls-Royce produces a good percentage of all the engines of airplanes. It's between 30 and 40%. And so it works with Airbus and Boeing mainly. And they don't sell engines, they borrow, and like Airbus and Boeing borrow the engines from Rolls-Royce, and Rolls-Royce still has to like take care of everything in the engine. So it has to take care of like any kind of maintenance, of inspections, and regular inspection, and repair if there is damage. So the main issue that we have with this is that if anything happens to an engine, we don't know it until we can actually see it. And like here on the slide, you can see what's inside an aero engine. There is like this huge turbine with a lot of like very extremely small blades in extremely cluttered, like small environments and passages. So how do we see it? Usually we take the engine, we disassemble the engine from the wing. We have to take it into a laboratory, open it up, and then we can properly inspect, check if there is damage, and repair the damage. And obviously you can imagine that this like requires the airplane to just stop. So when you have to repair an engine, you will have to keep the airplane down for, if you're lucky, one day, if you're not, maybe longer. And these are like huge costs. So what everyone would like is to have some kind of robots that are able to just enter this engine while it's on wing. That's why it's called on-wing repair, without disassembling it. And we have these robots going inside the turbine, exploring the entire volume, checking if there is any damage, anything that needs to be repaired. And if that happens, we want this robot to also be able to repair everything. What are our challenges? First of all, access parts. In order to enter an engine, we have to go through very, very narrow passages. Sometimes we have holes that can be as small as like 5-6 millimeters. And from these holes, we have to enter the engines and navigate through it for a length of 1, maybe 2 meters. So you can imagine that like it's not easy to design a mechanical system, a robot, or anything that can actually access and navigate throughout all the engine. Other issues that we have from an industrial point of view is that often we find ourselves in environments with extremely high temperatures. If we want to repair an aero engine, if we want to inspect an aero engine, for example, while it's working, we could be dealing with like temperatures of several hundreds of degrees. And the repair itself often could involve high temperatures. For example, we could have a flame spray needed, which can be at thousands of degrees. And another possible application is radioactivity. Like in nuclear facilities, we have radioactivity, and we have to take into account how radioactivity is going to affect our robots once it enters and explores. So what we propose in our laboratory is to use snake-like robots. So you can imagine these snakes that are extremely thin. I don't know if you can see my video. I have the body of one right now. They are extremely thin, extremely flexible, and they can be extremely long. They can be even some meters long. And we can insert these snake robots in the engines without having to disassemble the engine or open it. And once they're in, they can explore, find damage, and repair it. So the first robot that I want to show to you today is the shortest of our snake-like robots, which is a bore blending robot. The issue that we try to address with a bore blending robot is the fact that sometimes when you have the aero engine turbine moving, there are some debris or some like small items that enter, get sucked in the engine, hit a turbine blade, and damage it. When this happens, you usually have a chip, a very small damage that can create the beginning of a failure or crack. So in order to remove this failure, we have to take a grinding tool or a milling tool, and drill around this failure to make the surface smooth. The tool that we use, you can see it here, is the tip of this robot. And it's basically what dentists use to like grind your tooth when you have a tooth operation. So this robot, the aim of this robot is to have a robot that can be assembled onto the side of an aero engine. You can see it assembled on the side of an aero engine here, actually. So you take it, you attach it to the side of an engine, and the robot goes in. There is a very small camera on its tip. We find the damaged blade, and then we start drilling and removing some material from it. The main advantage of this robot is that it's teleoperated. So this kind of operation requires an extremely skilled operator manually like operating the grinding tool at the moment. And Rolls-Royce in particular has a very small numbers of operators, and they are all here, very close to here in Derby. It's 10, 20 minutes from here. And they could be called to operate on damaged aero engines everywhere in the world. So that's fine. I mean, if you have a damage, I don't know, in London, in Paris, that's easy. The operator just takes a train, maybe 2 hours, 3 hours, and it's there. But imagine having a plane stuck in Mexico City or in Australia. And in that case, you have to, at the moment, you have to physically take the operator, put him on a plane, and ship him to like another continent. And that can take days in which the airplane cannot move. And also like you need to like send a person for like days away for a repair that can be done in hours. So our idea is to have this robot being teleoperated from here, from like the Rolls-Royce headquarters in the UK, everywhere in the world. So you can just ship the robot or have the robot in main hubs and airports in all the continents, so that if a damage is found, you can, like anyone can just take the robot, attach it on, and then you have the skilled operator moving the robot from here. And here you can see some additional details of the robot. There is this large cylindrical body that is assembled outside of the engine. And its main role is that of guiding the smaller snake robot inside the engine. So it pushes the snake robot in and it rotates around its axis. And then you have the tip, which you can see here in detail, which has a stereo camera. It's driven by cables. So we have cables going through the body of the robot. And just by pulling cables, we can change the shape, control the shape of the tip. And there is the grinding tool at the end. And in this video, you can actually see the robot moving, working. So here you can see an operator attaching the robot, assembling the robot on the side. And this is what we actually see from the camera in the robot. And this guy here is our skilled operator from the UK that is still operating the robot from his own computer, which can be from the other side, like in the other side of the world. And here you can see the outside part that is pushing the robot in. You can see the tip of the robot entering. This is a camera inside the engine. And we start bending the tip until we find the damage that you can see here. Then once the operator has found the damage, we can use the camera on board, which is a 3D camera, to to reconstruct a 3D surface, and the operator can plan for the repair operation on this 3D surface, so it can simulate the motion before trying it. And once that's ready, you can see the robot just going in and slowly removing some material until the surface is smooth. Once the operation is done, the tip is just taken out, the robot is disassembled, and the repair is finished. So this is a robot that was developed up to 2017. We are currently working on a second generation of it, which should be ready by next year, hopefully. And it has been already tested on like real engines. But I was speaking of like snake-like robots, and you can see that this robot is like extremely short. Let me move on to a robot that might remind you more of a snake, so with a longer body. I'll show you first of all a simulation of a concept of a longer snake robot that is used for in situ coating repair. So this robot doesn't work on blades, but works on works in the combustion chamber of the engine instead, which is a like larger area, but being larger, it requires a very long robot, like more than 1 meter in, to like find damage, to inspect the entire area. And once it finds the damage, which in this case is a surface that needs some coating repair, it inspects it, it prepares it, and the surface is repaired by spraying a flame at several thousands of degrees on top of it for 20 to 40 minutes. Once the coating repair is done, we re-inspect again, check that everything is okay, and then go out. So in this case, what are the challenges? The challenges are different from the previous one. In the previous test, our main challenge was the length, the small passage, was that we had a very like small entrance to the engine. And the other challenge was that we needed teleoperation. In this application instead, first of all, we need a longer robot. We need a robot that is like more than 1 meter long. And also we're working with a flame that is like thousands of degrees and basically melts everything that's like, it will melt every kind of sensor that's on top of like equipped on that robot. So our solution, as you saw in the video, is to use 2 robots. One of the 2 robots has all the sensors. It has a camera, it has everything else that is needed for inspection, while our flame robot only carries the flame. So here in this video, you can see the navigation if it starts. Okay. So here in this video, you can see an actual prototype navigating in. It accesses from, again, a very small part on the side, and then it's slowly inserted in until we find the damaged part. This robot has 10 different sections. Each section of the robot is controlled by 2 or 3 cables. And overall, the robot is, this one is 550 millimeters long. We have 20 degrees of freedom in this robot. The tip of the robot instead has a flame, and here you can see it repairing the coating in an actual operation. This has been tested also on a real Rolls-Royce engine. And moving on from the aerospace industry, I'm going to present one last robot that works in the nuclear industry. Nuclear industry has different challenges when compared to the aerospace industries, but it's similar in many respects. So usually the spaces are a bit wider, but once we get into glove boxes or the actual nuclear reactor, there are a lot of very cluttered environments or pipes in which we need to navigate, that we need to inspect and check. And as you can imagine, conventional robots just don't behave well in these environments. Just imagine a pipe section, a lot of pipes with like bends and like maybe U-shaped like a U, and like a standard robot, first of all, cannot access if the pipe has a small diameter, and then it just cannot bend several times along its body unless it has an incredibly high number of degrees of freedom, like our robots. So our proposal for the nuclear industry is a slightly thicker robot. The diameter here is 20 millimeters, so 2 or 3 times the diameter of the aerospace one. And you can see it navigating in pipes, and thanks to its flexible body, can navigate around corners without any problem. And it has a hollow core. So inside of this robot, there is an empty channel through which we can bring cameras, we can bring tools, or we can control grip pairs or everything that we need. And you can see it as it navigates through complex environments, like its body shape can be changed to access different parts. It can be used to inspect ceilings as well, thing that like a lot of like flexible robots cannot do. And here you can see it just inspecting a typical item that can be found in nuclear environment. Here you see it just entering a bottle that's several meters away from the main body, which is something that's impossible for a conventional robot. And here it's exploring, inspecting a small item inside of a glove box mockup. So this robot is sort of similar to the ones that you've seen before. It's still like cable driven. It's still controlled by a certain number of cables, 24 in this case, going through its body, and just by pulling or pushing the cables or releasing the cables, you are able to change the shape of their sections. You can like see it easily. In my video, I'm holding a cable, and you can see that like as I pull or release the cable, the shape of the robot changes. So overall, here I like showed you a quick introduction on snake-like robots and how they can be used in different industries. I want to, in conclusion, the first thing that I want to say is that these technologies are becoming mature right now. So these things that you've seen are mostly at a research stage, and they have been demonstrated in real case scenarios, but they're not being used by industry yet. Rolls-Royce and other industries are planning to adopt these kind of technologies within 5 to 10 years. So what we're looking at now is like research that will have an industrial impact soon, but hasn't had it yet. Another thing that I want to point out is that I was presenting a single technological solution that can be applied to a variety of problems, but obviously this doesn't mean that like no other solution can be found. For example, I don't know if someone in the next year will maybe develop some kind of like swarm robots that are, I don't know, mosquito robots or insect robots that can easily crawl into the engines and perform the same repairs. So this is just like, I was just presenting the technological state of art on snake-like robots, but I'm not saying that this is the only solution to these kind of problems. And last thing that I wanted to add is that I've been told that some of you are biomedical students, and I want to add that like I only presented today industrial applications for snake-like robots, but they have been very successfully used in medical applications for surgery, because like their shape makes them perfect, makes them perfect to navigate inside the human body. There are plenty of works from the last, I'd say, 10 to 15 years about snake-like robots that have been used to inspect basically the human body, and also for intervention, for surgical intervention within the human body, mainly for brain surgery. And this was all for my presentation. I'm happy to take any kind of question that you might have. Please write them in the chat as Eduardo said, or like feel free to ask them in person as well.
Excelente. Excelente, Mateo. Gracias. Muy bien. Vamos con la sesión de preguntas. Bueno, ya tengo aquí unas preguntas. Bueno, primero que nada, voy a dar la palabra. Aquí levantó la mano Marco Zapata. Si gustas proceder con tu pregunta, por favor.
Yes, thank you. I have a question. What do you think is the hardest challenge while designing this kind of robots?
For us, so it depends on which kind of engineer you are. So if you're a mechanical engineer, the main challenge that you will find is to miniaturize everything. We have to deliver sensors, lasers, flames inside of an engine. And very often we have a very limited space to do it. If the axis, for example, if the axis part is like 5-6 millimeters, most of the space is actually taken just by the body of the robot. And the actual space that we have inside, so the central hole might be 2 or 3 millimeters only. So managing to like miniaturize both the tools and the robot is a huge challenge. The other challenge that we have is the control of these robots, because you can imagine just like they're very flexible, they're very long, the stiffness is not too high. So if there is something unexpected, like an obstacle, the robot can get stuck onto it, and like we could be moving its body without realizing that the tip is advancing. So control is a big issue, both from a modeling point of view and from a more practical point of view. These are our two main challenges at the moment. I will also say that there will be a third challenge later, in 3 to 5 years when they're actually adopted in industry, which is repeatability and just reliability. Because at the moment we're working on prototypes that are like tested for, I don't know, some hours, some days maximum, but like in the future, we want to see these robots to be used for years in an industrial setting. And we still don't know, like we're using cables to drive them. For example, we don't know if the cable will be able to like work for years or will just snap after, I don't know, 20, 30 hours of use. So these are the three main challenges.
Excelente. Excelente. Muy bien. Gracias. Siguiente pregunta. Vamos con la siguiente pregunta. Antonio Uribe escribe aquí, bueno, lo mandó en mensaje directo para mí. The radiation of the reactor don't produce a interference with the sensor of the robot?
So the radiation of the reactor does not, so we have tested mainly the robots in Glovebox where the radiation is not too high. So we haven't had issues with the sensors of the robot. Our real issue with radiation is the surface of the robot, because once you insert the robot in a radioactive setting, you have to take it out at some point, and you cannot just like take it out and like spread this like radioactivity everywhere. So to avoid this issue, we are thinking of using removable sleeves. Just imagine having a sort of like sleeve that you put on top of the robot before entering a radioactive area. You go around, you interact with the area, and before going out, you just remove the sleeve and throw the sleeve away. So the solution at the moment is a radioactive sheath.
Excellent. Excellent. Thank you. Thank you, Matteo. The next question is, what materials are snake robots made of?
So snake robots, it really depends on your application. Most of our first prototypes are usually 3D printed. We tend to use either high temperature resins or flexible resins to 3D print them. The prototypes that you saw in the videos are industrial prototypes, and their discs are made in titanium, while the cables are all steel cables. The flexible part of the snake robot, basically the backbone that goes through the entire body, is usually made in nitinol, which is a nickel titanium alloy, which is a super elastic material. But obviously materials might vary in other applications. For example, our main worry is to have the robot maintain its shape, be accurate. If you're designing a snake robot for surgical application, you're more worried about not hurting your patient and making sure that you're not inserting any toxic material inside the body.
Yes, of course. Thank you. Okay, Gabriela Telles, how much does one of these robots cost?
That's a bad question. The robot itself, it depends again on the material. The robot itself could be affordable. If you 3D print it, it's going to cost, I don't know, $100, $200 maybe. If you're going to make it in steel with like steel discs, the price might go up mainly for machining because it requires high precision machining, and it could go up to like thousands of dollars. If you're moving to titanium, the price can go much higher. And also the actuation pack, like the motors, usually have a significant cost. So it can range from like, I don't know, $100, $200 to tens of thousands or even hundreds of thousands of dollars.
Yes, because of the material. Yes, of course. Oh, okay, very well. Marco Morones, does this kind of snake robot can be handled by coordinates or only manual? I don't know if the question is explained.
I will try to reply, and then Marco can tell me if like I misunderstood the question.
Okay.
So both at the moment. So we can either create use standard path planning for autonomous motion and just tell the robot go to coordinate X, Y, Z, and the robot can just go there on its own, or we can teleoperate the robot. So just imagine using, I don't know, literally a game controller, and you move the robot with joysticks and buttons. Most of the actual operations are teleoperated, so are manually done, because it's really, really difficult to obtain an autonomous path planning for grinding operation or film spray. But the snake robot itself can function fully autonomously.
Okay, excellent. Okay. Yes, we hope you answered Marco Morones.
Marco, let us know in the chat if that was the answer.
Sí, es correcto.
Yeah, perfect.
Okay, perfecto.
Thank you.
Muy bien. Ok, me están pidiendo si también puedo hacer la traducción de las preguntas al español. Voy a intentarlo entonces.
You can actually write in Spanish. I will understand most of them.
Ok, muy bien. Ok, perfecto. Vamos con la siguiente. Creo que después venía la de Maximiliano. Max, ¿levantaste la mano?
Oh, yeah. The thing is, I was going to ask how long the lifespan of any of these robots is.
We haven't actually run an extended fatigue life test for these robots. Some of the our oldest robots are still working after 6 years of pretty constant use. The main issue that we have is cables. So the lifespan of the body of the robot itself is fine, but cables tend to break and snap after a certain amount of usage. It can be 1 week or 1 month. So they need constant repair and replacements, and that takes time at the moment. Replacing one cable can take 2 to 3 hours.
Oh, so the cables have a really short lifespan.
Yeah, the cables are the critical part of the system.
Okay, and is there any difference in between the ones that you use for radiation and the ones you use for aerospatial uses?
Cable-wise, no, we use steel cables for both of them. We are now testing braided cables as well. A lot of other research groups that work on snake robots use braided cables that are basically the ones that are used for fishing lines. And they tend to have a very good performance as well. Our main issue is that if we use braided cables, those are like, they tend to break on titanium discs because of friction.
Oh, okay. Thank you.
Excellent. Excellent. Thank you, Max. Vianey Gasca, what about the materials of the robots? Are those in the aerospace industry different from nuclear? Pregunta si son diferentes los materiales. Creo que comentaste.
They actually are. So if you see this one here, this is titanium and steel. So this one in particular is titanium because like temperature. Other of the aerospace are like just steel discs. And if instead you see this one, this is the nuclear one. This is just made in resin. It can be easily 3D printed because we don't have issues with like high temperatures or super high precision that's needed in the aerospace industry. It mainly depends not on the application, but on the size. Because if you're working in nuclear, you can keep the sizes bigger. So we can have the thickness of the disc of like 0.5 to 1 millimeters. In some of our aerospace application, we need some of the discs to be 0.2 millimeters thick. And like, if that's not done in titanium, it just breaks.
Okay. Excellent. Eduardo Gámez Castillo, how was the process of identifying the problem and the design or process of solving that problem? For example, about the snake robots.
Okay, so identifying the problem, the problem, well, everything started from aerospace. With Rolls-Royce basically asking us to find a solution to automate this inspection and maintenance. The way they did it, and they still do it, is by using borescopes, which are basically empty tubes, like flexible tubes with a camera at the end at the moment. So just imagine having this flexible tube, which is very similar to, I don't know, think of your charging cable for your phone. Like it's there, it's flexible, there's nothing inside. And imagine having a camera at the tip. So what they do at the moment is they take this borescope, they put it inside the engine, and they just like push it through until they manage to get to the place that they want. Obviously, you can imagine that like, one, this takes time. It takes a lot of like trial and error. And second, there are places with which you cannot just get with like a fully flexible tube. So our idea was to add cables inside it to control the shape of this robot automatically from outside. So that was how like the problem, I'd say that was part of the like identifying the problem and starting the design process.
Excellent. And
I hope this, yeah.
You also talk about you talk about insect design for new purposes, new robots.
I was like, yeah. So I was saying, yeah, basically we identified the problem. We tried to solve the problem in the easiest way possible, which is take a system that like people at Rolls-Royce are already used to, a borescope, and try to add a degree of autonomy to it. But like, I don't want to say that that's the only way to solve the problem. There have been attempts with swarm robotics as well, up to the moment unsuccessful, but we don't know if they're going to succeed in the future.
Excelente. Marco Zapata, tienes levantada la mano. ¿Tienes otra pregunta, Marco?
Yeah, I have another question. Well, it's kind of a hard one. Do you think in the near future, before approving these robots, do you can find a way to make them autonomous? Like you just place them on a part of the plane or the model and just fix it by yourself without needing someone to guide it?
We have autonomy already if needed. We like the robots can be guided autonomously already, and we can use conventional like SLAM methods. I'm not sure if you're familiar with SLAM. It's like simultaneous localization and mapping. It's a kind of like navigation algorithms that are currently used for mainly for mobile robots. So you can see them, for example, I don't know, in Boston Dynamics Spot. I don't know if you've seen it on YouTube. And like they can be, yeah, they can be applied. They can be applied to snake robots as well.
But I meant more like AI, like they don't need someone to tell them what to do and they just know what to do.
I can see this being possible. Like we already have, it's not science fiction. Like we have the technology to do it. We just haven't applied it to our robots yet. Our main focus is actually on the mechanical design, like mechanical design and low-level control. So before jumping onto that, we need to have a system that we know is reliable and accurate enough.
Excelente, muy bien. Gracias, Marco Zapata, por tu pregunta. Tenemos 1, 2, 3. Vamos a cerrar con Andriy, que levantó la mano. Entonces, para ir concluyendo, que ha estado muy, muy interesante y muy, muy llamativa la presentación, vamos a cerrar ya con estas 3 últimas preguntas. José Antonio, Arela, te lo leo en español. Esta tecnología es a las máquinas lo que el cateterismo y las sondas es al ser humano. ¿Combinan los conocimientos de ambas ramas para mejorar la tecnología? I don't know if it's well explained. It's like if it's well combined, these areas.
Can you repeat the question?
Is I don't know, I tried to make it in English. This technology is to the machines what is catheterism and the sondas to the human being.
Okay, yeah, what do you mean by sondas?
Sondas is like, I don't know what is the
probe.
Yes, probe.
Yeah, okay, that was like
and that's just for the open. And the question is this.
Yeah, no, the question. Yeah, I know the question.
Okay,
like I just missed that word, so it's probe
okay.
basically. Okay, yeah. So you mean combining the medical aspect and the industrial one?
Yes,
if I get it right, yeah.
Sí, creo que va por aquí.
We actually do it already. Like we are collaborating with like other research groups that work with medical robots to develop this kind of structure. We take inspiration from the human body and like medical robotics to develop even industrial structures, and they do the same with us.
Excellent. Okay, thank you. Naim Núñez, what extra knowledge or studies are necessary to work with this kind of robots, plus a robot-related career, of course?
Well, robotics in general requires scattered knowledge from mechanical engineering, electronics, mechatronics, some computer science, and sometimes even other fields. Like me, like I can speak for myself in particular. I am a mechanical engineer. So like I started as a purely mechanical engineer and slowly got knowledge in mechatronics and robotics during my master's and PhD. But you can basically get to this kind of like work or career from different like paths. You can get there from like biomedical, you can get there from electronics. You will just like focus on a different aspect.
Yes, Yes, of course. Excellent. Vamos con la última pregunta. Andrik, tienes levantada la mano.
Sí, well, first place, hi, Matteo. Well, I have a question, and in the sense, what about all mathematical calculations? Because I see that because in mechatronic engineering, we are learning about dynamic systems, and I would like to know if there is much to apply in this area, or if there is any software that takes care of most of these calculations. And because in one slideshow, I can see one diagram forces, and I don't know if you have some any plane about the robot with these kind of forces or these diagrams.
Yeah, so regarding the calculation part, I try to keep the presentation as like friendly as possible. So by showing you the videos and the systems and not like the actual mathematical expressions behind it, there is a lot of kinematics and dynamics behind this. Like basically the entire system is like requires a lot of like kinematic and dynamic modeling. And most of the research on snake-like robots is actually just on dynamics. And it's not a fully solved problem yet. So there are a lot of that kind of stuff behind this. I just haven't shown them in this presentation. If you want to have more information about this, feel free to like send me an email, and I can also like give you some papers or references for further info.
Okay, perfect. I tried to do one in my school.
Yep, perfect.
Excelente, Andrik, muchas gracias por tu pregunta. Muy bien, bueno, con esto finalizamos. Por último, comentarles que el doctor Mateo me hizo énfasis en que hay material de su investigación que está restringido, que no puede, por lo mismo que es trabajo en empresa Rolls-Royce, que no se puede compartir o no se puede difundir. Entonces, algún material está restringido. Él en esta presentación nos compartió el material que está disponible, que nos pudiera ser de mayor ayuda para comprender su trabajo de investigación. Ok, entonces, bueno, pues muchas gracias. Con esto finalizamos. No sé si tuviéramos algún comentario final o algo, pero con esto finalizaríamos. Le agradecemos al doctor Matteo Russo su presentación, que estuvo muy, muy interesante. La verdad, la verdad, yo también estaba esperando ver de qué trataba la conferencia para darme bien idea. Entonces, muy interesante. Muchas gracias, doctor. Daniel, no sé si tengas alguna pregunta, comentario final.
Gracias, doctor Eduardo. Pues muchísimas gracias, doctor Mateo. Fue una presentación muy interesante. Nos da mucho gusto que puedas compartir este proyecto con nuestros alumnos y ojalá esto sirva para motivarlos a ellos a ver, conocer en qué aplicaciones de la ingeniería ellos pueden pues comenzar a interesarse, saber hacia dónde pueden ellos comenzar a especializarse y ver hacia dónde quieren dirigir pues su futuro. Entonces, muchísimas gracias. Creo que ha sido una presentación demasiado interesante. Ojalá que los motive. Gracias de mi parte, sería todo. Agradecer a todos los alumnos que estuvieron presentes, docentes que nos acompañaron y en general a toda la comunidad de la Facultad de Ingeniería. Les agradecemos mucho por su tiempo. Y bueno, estén pendientes por ahí en un rato más, a la 1:30. Tendremos nuestra siguiente conferencia para que puedan por ahí hacer los ajustes y arreglos. Y todos los docentes ya conocen también este calendario para que puedan apoyarnos en motivar y permitir la asistencia de los alumnos a estas conferencias en la Semana de Ingenierías. Muchísimas gracias a todos y que tengan un excelente día. Doctor Mateo, en breve estaremos compartiendo contigo un reconocimiento por tu participación en esta presentación. Muchísimas gracias.
Muchísimas gracias a vosotros.
Excelente.
Thank you for inviting me. Yeah. Thank you all for listening as well.
Thank you, Mateo.